In this video we will have a look how to digitally reproduce this part. This is a car part originally made of injection plastic molding. Our plan is to 3D print it, to rapid prototype it. First we will use our scanner, Nikon Metrology MMD X50 scanner, together with a MCA20 measuring arm. We will gather with the scanner, we will gather a point cloud, then mesh it to form an STL model. Most probably we would need to scan it in two parts and then assemble the two STL parts separately, and also analyze and modify or edit the STL model so it would be watertight and would enable or lend itself to 3D printing. To do the scanning, we will use the Nikon Metrology Focus 11.0 metrology software. In this software we have the possibility to control our laser scanner and to scan the point clouds.
So now we start scanning to collect the point cloud. To keep the laser in focus, we have to keep the red dot and line together and move it so that it stays together.
Here we can see how the laser is collecting points from the part. The red line is the laser line, and the blue and green, these are representing the points that are gathered by the laser. So first we will form the geometry of the part as a point cloud. Right now we can see that we have formed a partial point cloud of the part. This is a line scanner, so the points are forming stripes. Now we can convert this point cloud to an STL model. This will take some time, and here we can see the STL model of our scanned part, and we can take it from here where we need to collect more points and so on. So here we can see that the first half or first part of our detail has been scanned. There might be some small holes still within our STL model, like for example within this opening there and in those corners, but we can get rid of them later when we do our editing of the STL model. Now we will continue with scanning the small portion of the part that was used to hold it within the vise. This one over here. The first STL is done. Here you can see that we have repositioned our part. This part, or this portion of the part that was initially used to hold it within the vise, this is what we are going to scan right now. And then we will put them together in digital form. This is now the completed section or still missing part of the scan. Here we have imported the STL model we have just scanned to another software. It is Geomagic Wrap. It is a software specially dedicated with working with the STL models. What we can see here is that we have several patches or several individual meshes that have been combined together. They haven't been actually stitched together in a sense, that they are still separate, and these are the separations lines. A couple of things we would like to do now. First, it is advisable that we get rid of the part we don't actually need. This here is the part that was used to hold it in vise. It is useful to get rid of that, and actually we can also cut away already some part from here. So to select those individual polygons, we will check whether we can select through. We will check back faces. Let's use the polygon selection tool, and let's see where we can end with this result. This choice here seems to be acceptable. Let's delete those polygons. This is fine. Now we will bring in the other part. We will import the other STL part here, and we will roughly align it first by eye. For that we will use the move tool. We will give it a rough inclination, how it should be here, and then we can use the alignment tools. In principle, this is the way they should be, and we can leave it as it is right now. Then we can go to alignment. This Geomagic is only one option. There are several other softwares available which will do it in principle the same way. So now we have the different parts, the two parts. We would need to set one as a fixed one. Let's say we take the bigger part will be set as a fixed one. The smaller one will be the moving one. And what we need to do now in this step, we need to indicate common points on both parts of the model. Obviously, let's say there is a point, over here is a point too, that are roughly on the same place at both models. Let's go to the other hole over there, and after 3 points you see there is already an alignment made. We can have some more points. Let's say take a couple from that surface over there, and let's register this. This is okay, and we see that now we have now our part is complete, and we can move on with other edits to this part. What we would like to do now would be to refine the alignment with a global registration automated refinement command. Let's put zero tolerance 0.1 millimeters. Let's see whether it can fine-tune the alignment, it did it. It looks fine, so we can click OK. This looks okay. Now we need to continue with working with the mesh. First of all, we would like to get rid of those separation lines. Those we go to Polygon tab, and in Polygon tab we will now go and merge the two meshes. Let's use the standard values over there, and let's merge it. Since our goal here is to end up with a reverse engineered part, we don't need to be that careful with our parameter values, meaning that if it goes a little bit off the accuracy of the geometry, it will be fine. We can tolerate in this case. Another thing we would need to do actually it is already doing it. It is already decimating in this with this command, with the merge command. It is also cutting down the number of triangles. Right now our mesh consists of roughly 1.4 million individual mesh pieces or triangles, and we are now telling it to cut it down to 100,000. Actually, with this particular scanner, with the Nikon scanner, its resolution is quite high, and it is advisable to use this 10% as a rule of thumb, meaning that we will only keep 10% of the original data. We have some problematic areas over here. This definitely is not looking nice right now. Something must have happened here. Let's see if we can get rid of it by utilizing the automated tools. Couple of other points we need to pay attention: the holes and etc. So now we will use the Mesh Doctor. This is an automated mesh improvement tool, and it did take care of some of the parts, but it again it failed over that location. One way we can try to solve this problem over here, we can try to select these facets and let's delete them. Let's take them away actually, and also delete this part from here. This is also not nice, and we can start to recreate these features. I will take away some more points from here. One more time, get rid of the individual floating bits by running a Mesh Doctor again, and then we can see whether we are able to recreate this part or not. What we can use here would be the fill single option with partial and with tangential option, and then we will take this one which created this part to a satisfactory level. We can use this, and it is already much better. And this way we need to now fill all of the gaps. It is a thin part, and the edges are somewhat problematic. Let's say if we can switch to fill all, might be a better solution this time. I will cancel it. Here is a possibly problematic area. First we'll get rid of those facets, and then we will try to, then what we can do, we can try to run the automatic hole filling tool one more time. This is to assist the tool. Let's run it one more time. What we have here again here, because we might end up with a scenario where this automated tool will delete or will try to fill the hole. This is something we don't want. Let's see, let's take fill all, let's use the curvature option and put there OK, and the holes are still there. Yeah, we have some problems over here, because in this region we see we have deleted, we have it has filled the hole, so we must now think what we can do over there to improve the situation. There are other tools that can be utilized here. Right now they are not important. We see there is now a problem here. There is a problem here. Let's see if we can recognize this as a surface. Okay, let's leave it. We need to work on this a little bit later on. So here is our mesh. In principle it should be now watertight, meaning that this is something we can actually feed into our slicing program, and then it can be 3D printed. What we can do additionally, we can think about in other scenarios we can think about aligning the part to the world coordinate origin. It is not that crucial in this world coordinate system. World origin is somewhere over there, and our part is in arbitrary position and in arbitrary location. Usually this is something to avoid, but right now, considering that our plan is to 3D print it, we can leave it as it is. What we can still do, what is recommended, we can try and we can go and see if we can enhance the situation with these two holes over there. Let's see how this can be done in another application software called SpaceClaim. It used to be SpaceClaim. It is a somewhat older license or version in here. Today I believe the software is operated under another name. So you see, this can be brought in from the other package directly, and we can also run the facets analysis in here. It says no problems found, it is watertight. We can run the other diagnostics tools. It should be okay. It should be okay and ready for printing. What was our plan? Our plan was to try to generate or let's say to enhance these holes over there. An option what we can do in this case would be to generate a kind of cylinder here using these facets. And then with those cylinders we can try to recreate those holes. Let's see, it might be a good idea to switch to the paint selection option, paint those over there. It is not that together. Now we can choose those facets. We can choose these facets, this one, and let's see if this is already sufficient for us to generate a cylinder. At least not here. No, the cylinder is not happening. So to recreate these holes here, we will first make a sketch on this surface. Right now the program is automatically selecting coplanar facets. We can start a sketch on that face. Let's have it on normal, and then what we can do here, we can utilize these section parts. We can use them, and actually based on them we can have a fit of arc. Let's do a fit of arc. Might be that the tolerance is too low right now. We will set this tolerance value up to 1 mil. Much better. You see, it is a continuous arc. 1 mil is perhaps too much. Let's try 0.5 millimeters. It is okay. 0.3 not okay. 0.4 not okay. 0.5. This is what we will use. Now we have an arc. We will go here and let's see. This one we will adjust by eye, the location of it, and based on this information let's create a circle. Most probably it is 8 millimeters circle, 8 millimeters circle, and this is now sufficient. What we will do from here, we will pull it to form a solid body. Let's pull it to form a solid body. Space claim is a direct modeler. We have this, and what now we can do additionally, we will move this body the cylinder we have just created. We will create a copy of it, and this is what we are going to adjust, so to say, by eye. In this particular case it is not that important. Let's look from that direction. I want to look from here. That would be the view command, and I would like to move this solid body. Move this solid body. Now the moving directions are a little bit off. So yes, we want to move it perpendicular. Again, choose the body, and now we can start to align it. Component, adjust direction, and now move the component. It is done by eye in this particular case. Here we can do that. It is important to understand when you can do these things and when you can't. Right now seems to be okay, because these are just two holes with a sufficient clearance and tolerance. We can do that. We have those holes in place. Now what we would like to do would be to get rid of these over here. These holes we will now fill. First let's delete couple of those from here. Delete this one. Delete this one. Let's say we have deleted them, and let's fill those holes. These are the areas to fill. Okay. We need to make them a little bit bigger, because now it went to the other direction. I would need to clear away some facets from there. Need to take away some facets from there and make it a little bit bigger, even more. Let's see if we can succeed in this way. Let's say what it will do now. Okay, need to come up with other means. You see, we managed to fill in the holes completely. Now we would like to utilize the two cylinders we have just made. Need to convert those into STLs, and then we can see if we can intersect the main STL body with those STLs, with those smaller cylinders, so that at the end they would form holes that we need. Let's hide the merged mesh, and let's take those two solid bodies. Let's convert them. You see, now we have three STL bodies in our file, and we can see if we can do the subtract command with the STL. This is the main one. This is the one, this body, STL body, is the one we would like to subtract from. These two are the cutters. and you see we have generated quite good looking. These are clear holes, and in this case they will suffice. In principle, similar procedures can be done with the other holes that we have on our model, but actually it might not be necessary. So we will leave them as they are, and we will move on with the rapid prototyping stage. This STL model is now considered ready for 3D printing. The final check will be done with the slicing program. In this video we will have a look how to divide up the STL file. The problem that we have with our STL is it is too big. Its size, dimension is too big for the printer to handle. We can try to estimate it over here. We can try to measure, analysis, distance, measure distance. We can check the distance. The overall rough distance is approximately 330 millimeters. This length over there. This is too much for the printer to handle, meaning that we would need to print this part out in separate pieces and then glue them together. So now we would like to have a look how to divide up the STL file. The first thing that is beneficial to do would be to align it, to align the STL to the coordinate world, to the coordinate system. Here is our coordinate system origin, and there is our part. We would need to conduct some kind of alignment. That is not crucial here, because there will be no comparison made. We are not going to compare nominal model against measured model to yield us some kind of measuring results. We just want to have this part in somewhat reasonable position. To do that, we can utilize the fact that we have a planar surface over there, so we can tell, or we can command the software to choose all those planar facets in this region, and then to establish a plane. Let's see, would it be better to do it over there? Yes, let's say we choose to create our reference plane over here. So let's clear out these facets. These are now cleared, and now we can choose those from there, and we can create a plane over there. This will be our plane 1. Okay, plane 1 done. So this we can establish as our XY plane, and for now we will also create another plane which will be a midplane between these two inclined planes. So let's take from there and add a plane, yes, and let's take from there and add another plane, yes. We have this plane. We need to these planes, as we can see, these are inclined. They are not perpendicular with the one we created first. So we now will create a midplane for those two. Plane 2, plane average would be the choice. Let's take plane number 2, plane number 3, apply. This is what we wanted. Okay. So we have now two planes we can use to align our parts. And to do that, we will go to align to world. We will choose the world coordinate system XY plane. That has to be aligned with our plane number 1, and then we will take XZ plane and we will align it with a plane we created as the last one. And let's see, here we can already spot there is some kind of let's see if we create this pair. Okay, it works satisfactory to our purposes right now. Let's okay. We will put it to isometric view. We can hide the features and we can see that this is now satisfactory. We have made a rough alignment that will ease our work while trying to separate this STL model into different pieces for the printing purposes. Now to divide it up to different pieces, it might be a good idea to actually make several copies of it. I will take the STL file, duplicate it, then we can get rid of the features here. No features needed for the copies anymore because those were just for alignment, and we can duplicate this one as well. And we can start cutting it into pieces. For this we will use the trim command, trim with plane. We will use the XZ plane, and here in principle we can try different values. We will need to move, let's try -45 millimeters. If we cut it from there, it seems to be okay. We have some distinctive features we can use later to glue this part together. Now we will separate them. We will get first rid of this bigger part, reverse selection, delete selection, and also we will utilize close intersection. And this will leave us with a clean cut on this surface, and we can save it out for printing. And in a similar manner we will cut out the other parts. Let's hide this. Let's take now this other version, repeat the trim command, repeat -45. This time we would like to keep the other delete selection, close selection, okay. We have this, what we already had, and now let's move it to +45 just to be a little bit symmetric. Delete that section, close that intersection, close. And here we have now the parts, the midsection. And following the same logic, we will separate the final section, meaning this section over here. And altogether we would have now 4 parts that we will print out separately and glue them back together later on. And this we had to do because of the physical limits of the working area of our 3D printer.